Hello everyone, and welcome to the A3 webinar series. Today's webinar is entitled Emerging 3D Vision Technologies. Thanks for joining us today. My name is Clarissa Carvalho, and I'm the Marketing Specialist for the Association for Advancing Automation. I'll be serving as your moderator today. Attendees doing this webinar are in listen-only mode, which means that you are muted. If you have questions during the webinar, please submit them in the question panel at the right of your screen. We will try to address as many questions as we can at the end of the program. If your question is not addressed during this webinar, we will respond via email. The webinar will be recorded and a link will be sent to you within the next 24 hours. For those of you who may be joining us for the first time or after a long while, the Association for Advancing Automation, also known as A3, is the umbrella association for the RIA, AIA, MCMA, and A3 Mexico. These four associations combined represent almost 1,300 automation manufacturers, component suppliers, system integrators, end users, research groups, and consulting firms from throughout the world that are driving automation forward. I would like to thank our sponsors of today's webinar. Matrox Imaging is an industry-leading supplier of component-level solutions recognized for providing OEMs and integrators with innovative yet cost-effective solutions. Their components include smart cameras, vision controllers, I/O cards, and frame grabbers, all specifically designed to decrease development time and cost while providing optimal price performance within a common software environment. Matrox Imaging technology is used by leaders in factory automation, process control, electronics, pharmaceutical production, packaging, semiconductor inspection, automotive manufacturing, robotics, and medical imaging industries. Lucid Vision Labs Incorporated designs and manufactures innovative machine vision cameras and components that utilize the latest technologies to deliver exceptional value to customers. Their compact, high-performance 2D and 3D Gig-E vision cameras are suited for a wide range of industries and applications, such as factory automation, medical, life sciences, and logistics. Their expertise combines deep industry experience with a passion for product quality, technology innovation, and customer service excellence. Lucid Vision Labs Incorporated was founded in January 2017 and is located in the Greater Vancouver area in Canada. IDS Imaging Development Systems GmbH is a leading manufacturer of digital industrial cameras with USB, Gig-E, and 3D cameras. With the brand new IDS NXT Ocean, they show how an easy-to-use inference camera solution for industry looks like. It includes not only the required hardware components, but also online access for intuitive training of neural networks for their own AI applications. Thanks to the cloud software IDS NXT Lighthouse, even non-specialists without any prior knowledge of artificial intelligence can train an AI classifier with their own image data and can be executed immediately on IDS NXT cameras. This makes it particularly easy to get started with deep learning-based image processing. Since it was founded as a two-person company back in 1997, IDS has developed into a successful, independent, and ISO-certified family company. There are approximately 300 employees around the world are real team players and work with joy and by conviction for you and your projects. Teledyne E2V is part of the Teledyne Imaging Group. Their innovations lead developments in healthcare, life sciences, space, transportation, defense and security, and industrial markets. Teledyne E2V's unique approach involves listening to the market and application challenges of customers and partnering with them to provide innovative, standard, semi-custom, or fully custom imaging solutions, bringing increased value to their systems. With more than 10 years of experience in 3D vision, Teledyne E2V provides a range of solutions from laser triangulation to time of flight, specially tailored for 3D application requirements. Thank you to our four sponsors for making this webinar possible today. I would now like to introduce our presenter for today's webinar. David Dekow is a globally recognized expert in machine vision integration and technologies. He is a principal vision systems architect for Integro Technologies Corporation, where he works with sales and engineering teams in the application evaluation and design of complex turnkey machine vision solutions. Prior to his position at Integro, he was staff engineer for intelligent robotics machine vision at Fanuc, and earlier was the founder, owner, and principal engineer for 2 successful machine vision systems integration firms. David is a recipient of the AIA Automated Imaging Achievement Award, honoring industry leaders for outstanding career contributions in industrial and scientific imaging. He is a member of the Automated Imaging Association Board of Directors and serves on the editorial advisory board of Vision Systems Design magazine. As a key educator within the industry for many years, David has participated in the training of hundreds of engineers as an instructor with the AIA Certified Vision Professional Program. He is well known for many of his informative technical articles, webinars, and conference sessions, which span a wide range of machine vision topics and technologies. Thank you, David, for being with us today, and I will now hand this webinar over to you.
Thank you very much, Clarissa. It's wonderful to be here with you and the A3 team for this very interesting webinar topic, one that is timely. 3D imaging is an important technology in machine vision and industrial automation, and a significantly growing technology in industrial automation. I hope that some of what we present here today will help you in your applications and perhaps give you some ideas as to how to use 3D imaging, 3D machine vision to make your processes more efficient, more reliable, and let's say more fun too. You can see our abstract there on the screen, and this is what we'll be going over. A review of 3D machine vision. I think we have a large audience, and I'd like to make sure that we know the background of what we're talking about when we mention 3D machine vision. Some of the evolving technologies and components, advances, a few implementation notes, and what's coming up in the future. Just a quick disclaimer. 2 items. First of all, our discussion, our association is an association for automating and advancing automation. So the context in which I'm discussing 3D imaging will be within the context of industrial automation and advancing automation in industrial environments. Don't be mistaken though. 3D imaging has a lot of other use cases, just a ton of markets where it can be beneficial. And for the purpose of our discussion, though, we'll focus on this industrial environment. Also, finally, in the introduction here, I always like to say that I do use many images, and we'll discuss technologies from different manufacturers, different vendors within the marketplace. I'm not intending those to be commercializations of the products, but all of our vendors and all of our sponsors have wonderful, wonderful 3D products. I hope you'll take a look at them. If I have missed in any way in any of the slides your favorite vendor or said something that doesn't make sense, please drop me a note, and we'll talk about that. And also, as we go through, please enter your questions in the questions box. We want to get to as many as we can, and with a large audience, we're going to allow a little bit of extra time at the end to cover your questions. So let's start with a 3D machine vision review. Going over the concepts of 3D machine vision in the context that we're discussing it today. So really, when we think about practical 3D imaging for automation, it's one of those many machine vision tools that enabled what the marketplace is now calling Industry 4.0, reliable autonomous automation, the ability to have smarter factories, better production, better efficiencies in production. This is what the industrial marketplace is looking for, and it goes without saying that machine vision and its close partners in technology, robotics, and other automation technologies have been at the forefront of driving these concepts in Industry 4.0, and all are data driven, all are data consuming, and machine vision machine vision, and particularly 3D machine vision, is certainly here to stay as a key component of smart manufacturing industry 4.0. So that's our context as we think about practical 3D imaging in our particular environment. The thing when we think about 3D imaging and really asking the question why use 3D imaging? The fundamental point, and I think this gets lost in the translation sometimes as we talk about the 3D imaging technologies, is that the entire point of 3D imaging is to provide us some content, some data in the image that comes from a different place than just grayscale or color content, the kind of content you would find in standard 2D imaging in machine vision. 3D imaging gives us data content that has the height, or let's maybe call it the profile, of the objects, the features, the parts, the things in the image that we're going to analyze. And that information is just extremely useful in many cases and almost required in certain use cases in industrial imaging. So it's an enabler, and it is a unique way to extract information, to see information in an image. So it's not, we're not just talking about getting that 3D image, but we want to keep in the back of our minds that we want that height or profile information from the 3D image so that we can use that in our processing. Now, how do we typically use this information? Well, in general, many of the things that you might think of in 2D machine vision in an industrial environment lend themselves to 3D imaging. Again, in that context where we're working primarily with, or we're working for the main point of our working being with the height and profile information. So the ability to look at feature and object geometries for measurement, identification, quality inspection, except that we have the ability to see that in 3D. We can differentiate, we can extract information based on the height and planar information of the object that we see, rather than having to segment it based on contrast. Of course, one of the key uses for 3D imaging is real-world object orientation. It may not just be for robotic guidance, maybe for location or other purposes, but that's of course a key capability of 3D imaging in automation. So what are the basic what is the basic 3D information that we get? Not just thinking of it as a pretty picture, but thinking of the data and how that data is used in the image. All of the data in a 3D image are points in a world coordinate frame. Now, we'll skip the fact for now that frame may be just the camera. It may be an arbitrary relationship in world coordinates, but nonetheless, all of the data are these 3D points in a world coordinate frame. And then in processing, the information must be combined or isolated to form geometric structures so that we can do those application tasks that I just mentioned, utilizing that data. Perhaps extract the features, perform measurements, as we said, provide locations, and much, much more. Keeping in mind that this is all then based on segmentation of these features, not utilizing grayscale, but utilizing height and planar and other primitive geometric information from that 3D image. A quick word on how the images are represented. I think this is one of the things that first time users of 3D machine vision, or folks who are just entering into the 3D machine vision space get a little bit confused and not quite sure of what we are seeing when we look at the 3D images. The vendors of 3D components, the people who create the software and provide the software, all provide wonderful visualizations of the 3D data. But the point remains is, I guess the point I would like to make here is that these are visualizations and not necessarily the raw data that's being used in your application. Let's look at the image, for example, to the right. One of the images I took in our lab for a while back. We can see almost the outline of an engine head there, and it looks to the naked eye sort of like an engine head, but that is a 3D representation. However, it's been enhanced by overlaying or associating a 2D grayscale image with that 3D information. If we look at the raw 3D information to the bottom of that image, which is in this case is a depth map. If we wanted to name the image above it, it would be a rendered surface. The data are much different from what you see in the pretty pictures that are displayed in 3D imaging, let's say marketing, and even for human consumption. And the types, some of the types of scenes that you'll hear or images you'll hear mentioned are point clouds, textured scenes, rendered surfaces, and as I mentioned, even depth maps, and there are more. But I want you to understand that these are, I take away with you that these are representations of the 3D data, and the 3D data that we work with in the actual applications is much more basic than that, much more primitive than that. It may be it certainly is point clouds, depth maps, but each of these features, each of the points, each of the point representations has to be processed as a raw image, and not in the way that you see it represented in a 3D scene in some of these texture or rendered surfaces. So with that, a quick review of how machine vision works within the automation environment. I'd like to move on to some of the evolving technologies and components, and in this context, continue a little bit in our discussion of reviewing what 3D machine vision is and how 3D machine vision works in actual practice. The name of our webinar today being Evolving Emerging 3D Machine Vision. I wanted to kind of take that and describe what I think we're experiencing in terms of evolving technologies and components. And one of the big things that's evolving right now is not so much the technology, although I'm going to discuss some of the things I think are really moving forward in technology. But the one thing that I think is a strong evolution is the marketplace evolution. We're seeing continued growth in the marketplace, and by marketplace, that means those people who are supplying components, supplying technology to those of us as end users. There's continued growth, continued advances in these 3D imaging components and technology, and that marketplace growth is not only, I think, the most interesting growth and interesting evolution in 3D machine vision, but also one that is really going to benefit us moving forward as we find more vendors working to deliver better and better technologies that are applicable to more end use cases. I think that we're going to see higher usage of 3D machine vision, higher reliability, and less end user concerns about implementing 3D machine vision. So keep an eye out for that. I think that even in a period of several months, we see continued changes in what the marketplace is offering in 3D machine vision and ways that you can use it in your applications. So having said that, let's look at some of the technologies, look at some of the components. And the place to start is to understand the role of 3D imaging components. And that I think primarily, and again, one of the things that gets perhaps lost in the translation sometimes is that a 3D machine vision camera or a 3D machine vision imaging system is primarily an image acquisition device. I'm not going to call it a dumb camera. I'm not going to compare it to a dumb camera, but I'm going to, I want to comment that it is, the device is there primarily for image acquisition and to provide, as we'll learn later, a group of images that when combined or when processed can create a 3D scene that ultimately you can work with. So given that we're going to think of this 3D camera, 3D imaging system as a acquisition device, what are some of the differentiators? One of the big differentiators in the marketplace is the technique used to capture that 3D information. And sometimes, depending on the technique, you're able to relate a technique, I should say, to specific use cases for your applications. Some techniques lend themselves to certain applications. Some techniques, imaging techniques, just plain don't lend themselves to those applications. And we're going to mention those as we go along here. Another differentiator in the components and the technologies available in the marketplace are some other features and capabilities of the system, and you have to look to the individual components to kind of identify and maybe make your own evaluation about the importance of these features and capabilities relative to your application. One of the big ones, I think, and we're going to mention this later, is the method, the software, the firmware used to create the 3D image, or ultimately the 3D images, depending on the technology. How do those images get created from raw, frankly, 2D or raw plain images and turned into a usable 3D image for our processing? It varies by technology, it varies by component, and that's an important part that may be of interest for your particular application. Some applications are dependent upon speed of acquisition, the speed of processing, and that may be a consideration that differentiates one component from another in your applications. Perhaps what other image data formats are available. One of the great new evolving features of machine vision, of 3D machine vision, is the capability of a 3D machine vision component to deliver not just a 3D, shall we say, point cloud, depth map, depending on the component, but also to deliver perhaps grayscale image, a matching grayscale image, or matching rectified grayscale image, or perhaps a rectified color image, or other spectral imaging, perhaps near IR, in 2D that is spatially matched to the 3D image itself. And that may not be a requirement of your application, but one of those potentially differentiating features and capabilities. And there are many others. I would just add too that certainly physical properties, in my experience, form factors of the component can drive the decision making and the differentiation of an individual component. If your application involves robot guidance, it may be as simple a consideration as whether or not your robot has the payload capacity to put the and you need it on the end of arm, is whether or not your robot has the payload capacity to put a 3D imaging device on the end of arm, or a specific 3D imaging device. All of these things come into play, and more certainly. But keep in mind the role of the 3D imaging component is primarily image acquisition. So how do these things acquire an image? This may be review for some of you, but I think it's important to both review and to present for folks who maybe haven't heard these general categories of 3D imaging techniques. First of all, one of the most basic 3D imaging techniques is just stereo 3D, binocular imaging with two cameras calibrated together, spaced at a calibrated distance apart, or at least calibrated to the distance they're spaced apart, and taking each camera taking a normal grayscale image, and then using 3D image processing techniques to combine those images into a set of 3D points. Well, I'll mention in a minute what some of those techniques are, but in the most simplest way, we can call this a triangulation and comparison of the objects seen in the two cameras which have slightly different fields of view, and the disparity between those two views. We'll find later that a disparity image is one of the things that's produced in this kind of a context. This kind of imaging at this basic level is another term for it is called passive stereo image or passive 3D imaging, because nothing else is happening except the grayscale cameras are taking the image with whatever lighting, whatever passive lighting is applied to the scene in order to make the image appear in the 2D image. Very basic, but very successful type of 3D imaging task. I've found in a couple of applications that passive stereo 3D imaging actually can be more effective than some of the other possibly more what we might call more advanced 3D imaging techniques because of certain characteristics of the surfaces you're going to inspect. But we'll call that a basic stereo imaging technique, and then move to another very popular and widely used technique, and that is structured light. Now, when we're thinking of this as a stereo camera or even a single camera, this is kind of sometimes generically referred to as active 3D imaging. Now, if you think about going back to think about the binocular stereo or the two camera stereo imaging, if we're looking at objects that don't have any texture, what we would call texture in the 3D imaging context is features in a grayscale contrast context that help to identify correlated objects from one camera to the other. Think of trying to look at a bare wall, a blank wall, and judge the distance to that wall if you have no other references. The same thing happens in 3D stereo or 3D imaging, in that if we don't have references to the surface that we're imaging, if we don't have references to the content on that surface, one of the ways to overcome it is to provide your own references, and that's done by aiming structured light at the objects. And that structured light comes in a variety of forms. It could be what we see in the middle there, structured coded light, using different encoding techniques to provide different patterns on the image. It could be to the right, random, or we might call it pseudo-random dots or other projected features that add texture to the image. And this is a pretty classic technique for 3D imaging, using either one or in some cases just a single camera, depending on how that structured light is implemented. We see a lot of products in the marketplace utilizing structured light, and it's a very efficient and also can be a very accurate way to gain a 3D image, and without much additional componentry beyond the cameras and the lighting, a lighting projector or the structured light projector. A whole different class of 3D imaging in terms of imaging techniques is laser triangulation devices. Once again, I'm going through some pretty common and widely used 3D imaging techniques, and laser triangulation are sometimes called in the 3D world sheet of light analysis. Simply uses a laser line. I take back. I don't want to say simply, because it's by no means completely simple, but it is simple to understand. We use a laser line and a camera at an angle relative to the laser line, and if you use your imagination, you can see that as that laser line encounters objects of different height, the position of the laser line in the image relative to the object and its background will change. Now, as the camera is calibrated and physically aligned with the laser line, that camera will start to see that laser line in different places, in different spots in the image, and you can triangulate, knowing the proper calibration or having a pre-calibrated sensor. You can triangulate exactly where that laser line is relative to height by seeing where it is relative to the vertical location in the image itself. In this case, this is a scanning technology where the part or the triangulation device has to be moving as it takes its image, but it's a very efficient device and a very accurate device, having some capabilities in many cases to achieve better accuracy than the first two methods we just discussed. And in going over some of these basic capabilities, or basic 3D imaging techniques, one I'd like to include that at one point was considered a truly cutting edge technique, but is falling more, I think, into very mature 3D technology, very reliable, very usable 3D technology, and that's time of flight. Now, it may be oversimplification. I'll state that it is definitely oversimplification to say that a time of flight camera measures the time between a light being sent out and the time it returns to the sensor. We're not time of flight cameras do not actually count or measure the speed of light, but through different techniques, either pulsing lights or modulating the light in phases, time of flight cameras are able to look at to compare the light going out relative to the reflected light, and by doing so, for each individual pixel on the sensor, create or analyze a distance of that light, a distance that light's traveled relative to the sensor itself. The 3D time of flight cameras provide 3D images similar to stereo or structured light images. They just do it in a little bit different way. These products are becoming more readily available and at cheaper prices, mainly due to the development by a sensor manufacturer, Sony, of a native onboard sensor, imaging sensor that is able to be incorporated in the cameras that has on board its own time of flight processing. So time of flight, I think, is one of those interesting technologies providing 3D information, but and no longer a cutting edge technology, but more of a mature technology in the 3D realm. And it wouldn't be complete if we didn't talk about the aspect of image acquisition software in 3D imaging techniques. Why do I group software in with the 3D imaging components? And the reason is the software is absolutely required in order to create the 3D image from a grayscale image. Some of the things that have to be done, of course, are calibration of the camera relative to its scene, so that regardless of the type of inspection, calibration of the camera so that it can, in the case of stereo or structured light, or stereo structured light or sheet of light, so that it can relate those grayscale information to a 3D image. Some of the execution techniques would be image rectification. That's matching the images, the left and right images, to each other. Creating a disparity map. I mentioned that disparity is the difference between the observed location of the object in one image to the observed location of the object in other. These apply to stereo structured light. In the sheet of light imaging technique, the software has to combine the individual lines that are taken as the part's moving past the sensor or the sensor's moving over the part. And that combination and then also translation of the position of the sensor relative to its actual Z height is a function of software, not accomplished by the imaging system itself. And then the creation ultimately of what you end up using in your applications, perhaps a depth map, an XYZ image, perhaps even a point cloud. That kind of processing, again, has to be accomplished through 3D software. The good news is that we find both SDKs and, as we'll talk in a minute, even onboard software that performs these in our marketplace very, very well and very efficiently. How about a couple of emerging now 3D imaging techniques? I've mentioned these other techniques for reference, and they are the techniques that I think are more fundamental and more mature in the marketplace. Some of the newer techniques, one combinational, or what the market calls computational imaging. You can do a lot of things with this, and the baseline premise of computational imaging is that you combine, and that's why it's sometimes called combinational, but you combine multiple images, usually at least 4, but sometimes more, to create a 3D image in a variety of ways. One of the classics and one of the most widely used, or in this new technology, I should say new technology, but in this emerging technology, is photometric 3D. Certainly something that's been around a long time, but becoming much more popularized by the readily available lighting techniques and readily available software to do photometric 3D. Shape from focus is another possibility with computational imaging, and even 3D from polarization. One of the some of the newer cameras on the marketplace are called polarizing cameras, and they through their sensor provide 4 different polarization angles in the image, and 3D shapes can actually be discerned from manipulating those 4 polarized images. What about some others? Perhaps LiDAR. The Sony RealSense camera that has long been a stereo structured light camera is now available with LiDAR instead of pure grayscale imaging to create the 3D image. LiDAR being, of course, a ranging imaging technique using lasers, and has been quite broadly used in autonomous driving vehicles. Or also other multi-sensing. We can think of a variety of ways that we can use multiple sensors with either single grayscale cameras or multiple grayscale cameras to provide 3D data. This may be a little more application specific, but certainly is a possibility. And we see multi-sensing, it gets talked about a lot in emerging possibilities for getting a 3D scene, or for even just enhancing a 3D scene in practical applications. Another kind of emerging technology, or emerging part of the technology, is the idea of using embedded components, embedded software for the 3D imaging task. I show a picture up here of the Intel, I think I said Sony earlier, but excuse me for that mistake, the Intel RealSense. And that camera is essentially an embedded 3D camera. It's all self-contained, produces its images, depth images, point cloud images, all with onboard processing, and delivers them. Now, I'm not recommending that this more consumer grade camera is usable for industrial environments, but this is an example of embedding software. Another example is in an Insenso product and other products, but we see to the left here, where you can pull the image, the raw images in off of the camera, and have a host PC manipulate them. But a trend nowadays is to bring, an emerging trend is to bring the processing on board the camera to provide the raw data necessary to ultimately get that image get that 3D image into the host PC. And of course, physical embedded components or physical embedding of computing and the component itself is going on a lot in cameras in both 2D and 3D. We see an example of a Lucid 3D time of flight camera that's in an embedded format where the camera attaches directly to an embedded type of processor board and then can be integrated in a more OEM environment or a more OEM product. Let's take just a moment to talk about applications. Now, I'm not going to hit on specific applications, but I just want to give a general overview and concept of the application environment. The bottom line is that as I started out the discussion, the application environment is just widespread for 3D imaging, and I think that as we all get more comfortable, as the end users get more comfortable with 3D imaging, we will find more and more 3D imaging use cases in the industrial workspace. I think they're there already. I think it's just a matter of accepting the possibility of using 3D in those cases. And I mentioned a few here. This is pretty straightforward. Guidance, of course, is a well-known task where we could benefit from 3D imaging and robotic guidance. Measurement, when we need to measure things that are not so reliably imaged in a 2D environment. Reconstruction of images for CAD modeling, even just generalized inspection. All of these lend themselves very, very well to 3D imaging. But as I said, the implementations vary widely. And one of the advances I think we're seeing, one of the advances that I see and I can be confident of in the current marketplace in applications and in software is that the software is becoming, the direction the software is taking us to more capable 3D software, more widespread availability of 3D software, and the development by some manufacturers of more configurable application-based software, so that typical tasks are more automated and more easy to use. The decision you have to make in 3D imaging is, are you going to go down a path of programming, or are you going to try to go down a path of configuration? If you're doing programming, many libraries exist. I should say a few libraries exist in the marketplace that are extremely capable and target themselves for providing 3D imaging capabilities for industrial applications. And they're not only expanding in availability, but also there's an expansion of available tools and the ease of use of these tools. Let's say the making macro tools that allow you to do allow you to program more easily typical industrial automation functions using the 3D images. There are also these configurable software packages that allow you to select the type of tools you want to use, but don't constrain you to a specific application. And I find that those are growing more in popularity, and we're seeing more of them in the marketplace. We see an example down here from Matrox and their Design Assistant product. And then finally, the application-based software I mentioned, where if you want to do bin picking, or if you want to do robotic guidance and bin picking, you will be able to go out, you are able to go out now and find an application that is a configurable application that allows you to do bin picking in a somewhat constrained way. But I think we'll see more and more of that, and that's where our application environment will advance in 3D machine vision for industrial automation. Let's conclude with just a couple of implementation notes. We didn't get a lot into the differentiation and selection of components, but let me just leave you with a couple of thoughts. The technologies, as I said earlier, vary widely, and the suitability for a given application varies in the same way. Some 3D imaging technologies are more application specific and lend themselves to a certain application. Some are more generic. And it would be a whole nother webinar to discuss which are which for a specific application, but I'd like you to take back with you the idea that you have to consider what is best for your application. Just a couple of generalities that may help you think about this. And this is just, again, very much a generality, not a fact for all components, but the potential depth resolution and height accuracy varies between products. Traditionally, time of flight and some other different applications like depth from focus or photogrammetry tend to be a slightly less height accuracy than might be achieved from stereo cameras or structured light or sheet of light systems. Interferometry, which we didn't discuss, which is more of an offline 3D imaging technique, being one of the higher accuracy 3D imaging techniques. The field of view also kind of comes into play with all of these, and you'll notice it tends to go in the opposite direction, where the high accuracy interferometry has by far the smallest field of view, and as we move along to getting into larger and larger fields of view, we go into technologies like the photometric imaging, sheet of light imaging, some of the other imaging techniques, stereo cameras and structured light, with time of flight to some extent, again, as a general observation only, generally has a larger field of view capability than some of the other technologies. Finally, a few other considerations: part movement and presentation. I already mentioned that one of the technologies requires part movement, and so if that's the technology that's suitable for your application, certainly the sensor or the object has to be in motion. Other technologies are not tolerant at all of part movement, and in those cases, small amounts of movement of the part during the imaging is actually going to impact your accuracy and impact your capabilities. Sometimes variation in part presentation will impact the accuracy, and as I mentioned, some systems use movable light and multiple images, and that being particularly in the structured light imaging, where sometimes motion can't be accounted for because of the multi-image acquisition. All 3D systems have a potential for a certain amount of loss of 3D information. How do you figure this out, or how do you consider this? You can take a quick look at the image to the lower right there, and I'm not picking on the laser line projectors, but this is just an example. Whether it's sheet of light, laser line triangulation, or even time of flight, the object can be partially occluded by from its illumination or by the angle of the camera for full 3D representation. And this happens in almost all applications to a certain extent. And as you specify and consider your 3D application, it's an important thing to keep in mind. And finally, a limit in 3D, it's still a surface analysis imaging technique. Now, I had a customer at one point take a look at my 3D imaging as I was processing it and say, I thought this was 3D imaging. How come I'm not seeing all the way around that object? Well, for many of you that may go without saying, but the camera is looking at a surface view of that object. The camera in one orientation, in one planar orientation, certainly is not going to see around the object, and it's not going to extrapolate it 3D information on the sides of the object or on parts of the object that are hidden. So in all cases, unless we're applying many cameras all the way around an object, in practical use, the camera is still a surface analysis, or the 3D image is still a surface analysis imaging technique. Even though we can see from that planar orientation the feature depth and feature depth contrast, it still is a surface analysis technique. All in all, successful imaging is sometimes complicated. I think that The maturity of the imaging in the marketplace makes it something that is becoming easier and easier to use and will be more and more applicable to your application. So a couple conclusions. As I said, it's really a mature and still growing technology, and it enables so many things that are better than 2D imaging. I think we'll continue to find more and more use cases for 3D vision. What's next? As I mentioned earlier, I think we're still going to see more components, more offerings, additional software capabilities, and even more advanced applications in software from vendors and manufacturers of 3D devices. The challenges still exist. It is a more complex, I don't mean to scare you away, but it's a more complex technology than simple 2D imaging. We have to be careful to apply it in appropriate use cases. And I get this comment a lot: is it really needed if I can do 2D contrast imaging sufficiently? And I guess the answer is it may be not needed when that's sufficient, but could you improve your reliability if you used, in particular cases, 3D imaging versus 2D contrast imaging alone? That's for you to decide. And with that, I'd like to move along to our questions, if I can, please.
Thank you, David. To our live attendee listeners, please submit any questions you may have at this time using the questions panel at the right of your screen. Several questions have already been submitted, so David, here is your first question. What must be taken into account when using 3D machine vision for robotic guidance?
Good question. It kind of gets us into a very specific application case. The main thing to be taken, I think, in 3D guidance for robotics, and I briefly didn't get into all the details, but briefly mentioned calibration. Certainly, it goes perhaps is intuitive that a 3D imaging system has to be calibrated to a world coordinate system that makes sense to your application. In robotic guidance, if I were to pick one of the key things that has to be taken into account and addressed, and that is the concept that the 3D imaging system has to match the robot coordinate system and not just an arbitrary world coordinate base. There are techniques, there are additional calibration techniques necessary in order to calibrate the 3D machine vision system to the robot world. One of the terms for this is called hand-eye calibration, which means that if we have a robot with a gripper, we need to calibrate that robot hand with the 3D imaging system. And that will be fairly straightforward in most 3D systems. Many software packages and 3D libraries and even 3D applications give you techniques to perform that hand-eye calibration. But other than the additional calibration, not much changes when you're working with robots and robot guidance. Certainly, anytime you put a camera on a robot, you have some additional challenges. Is the robot in the way of the camera? If it's robot mounted camera, I have to stop the robot to take the picture before I go and grip something. A lot of other considerations that we could talk about in depth at some time. But I think the main thing to think about is it's not that different, but it requires additional calibration.
Thank you, David. Your second question is there a trade-off between speed of scan versus clarity of the image it captures?
Let's define, I understand the question, and for others, let's kind of define that quickly. Speed of scan, that term could be used in a variety of ways. And so let's look at a couple here. If we're talking about a sheet of light camera, and I mentioned a couple of times that a laser line triangulation imager or sheet of light imager must have the part in motion. and that's sometimes called scanning the 3D image. The other way we might think of scan is that some 3D imagers, particularly those that do multi-image acquisition in order to acquire the 3D image, some of those use multiple projections of light, as I mentioned in structured light, use multiple projections of light to gain a single image. So if I take both of those separately, the question about clarity of the image and speed of scan. In the case of the laser triangulation scanner that has to be moving, there's no downside to moving that fast, other than the scanner, you must maintain a rate of capture that provides the correct image format in the direction of travel, and doesn't exceed the capability of the camera to acquire the images at that speed. So there's no clarity lost, but there will be limitations in how fast that camera can move relative to the required rate of acquisition, and that's necessary for the application to get the correct image and the capability of the camera. In terms of other types of 3D imaging systems that, let's say, scan the object, the rate of scan or the speed of the scan has to do with the number of images being taken, and of course some other factors like the ability of the system to the speed of the sensor itself to in terms of its frames per second, and the amount of exposure, which is additive to the frames per second capability of the camera. And that also kind of brings into account things like the resolution. Higher resolution sensors are going to scan or are going to take an image more slowly. But in that context, if we look at that whole process as one scan, not just the individual images, the whole process is one scan, I would say that to the questioner's comment, does the speed of scan affect clarity? The answer in that case is probably yes. And by that I mean in images that are able to do that rely on multiple images, the more images you acquire to a certain point, but the more diverse images you acquire with varying projected light in a structured light environment, the higher the clarity of the image, the higher the clarity of the 3D image. So in that case, you will get greater clarity in the overall scan, not the individual image acquisition, but in the overall scan, you'll get higher clarity by adding more images to the scan, and therefore that does reduce the speed of the scan.
Thank you, David. And this will be our last question. What industries are you seeing accepting 3D imaging for guidance applications, and how mature is this?
So I've mentioned that I think the 3D imaging is quite mature as a technology, but a competing comment would be that the acceptance of 3D imaging and the implementation of 3D imaging is lagging behind. I consider lagging behind its capabilities. I think there is some reticence in accepting 3D imaging as a solution, probably because of it's still a relatively new technology, and only something that's been growing in the past 10 to 15 years. And well, let's be honest, 3D imaging has been around since the first machine vision systems, but the mainstream 3D imaging for industrial automation has kind of popped up and grown over 10, 15 or plus years. And maybe that's not enough for the marketplace to accept it. Certainly there were some missteps early in 3D imaging where it was applied in ways that really didn't suit the imaging technique and really didn't provide the results that were correct. But I think that there are a wide variety of industries that really can benefit from 3D imaging and should be as we move forward, we should find them more accepting of 3D imaging. So that's my comment on how mature is it, and the idea of acceptance. What are those industries? I would say certainly heavy industry. Applications, and it's been in 3D imaging has been in use again for many years in heavy industry, particularly automotive, where the robots are guided to do all sorts of assembly processes on a car, and in other similar types of industries as well. But I think that's actual random 3D guidance in heavy industry is something that we're going to see growth in and continued acceptance. If I were to put out a buzzword, I would say the buzzword is bin picking. The capability of a robot to pick in certain cases, but the capability of 3D imaging to guide a robot to pick randomly oriented homogeneous parts, that is parts that are all the same in a bin or in a stack or in a pile, is quite mature, and it does work. I think that it just has to come into its own in certain industries. Take, for example, machine tending. The idea of the robot, of a unfinished parts in a bin, and the robot through 3D guidance picking those randomly oriented unfinished parts out of the bin and putting them into the machining center or the CNC machine. I think there's a lot of opportunity for that. I think it is mature and ready for prime time for those types of applications, as well as many other industries. One that immediately comes to mind too is the logistics industry. 3D guidance for palletizing, for depalletizing, box picking, even again, I'll call it homogeneous random object pick, is pretty much ready for prime time. I'll give you a little hint about 3D imaging here relative to that question and relative to that specific application and use case. What do you think is easier for a robot to pick? A organized stack with 3D imaging, an organized stack of boxes, or a random pile of boxes that are all mixed up in different orientations? I think intuitively, a lot of people would say, oh, well, it ought to be really easy to guide a robot to a nicely stacked pallet of boxes. The answer, though, is exactly the opposite. You see a lot of these demos you can look at a lot of manufacturer sites and see a lot of demos of 3D imaging guiding robots or looking at objects that are pretty much homogeneous, like boxes or all the same object in one stack, but the objects are all randomly oriented. Believe it or not, that's much easier than picking the objects when they're tightly packed and next to each other in 3D imaging. So those are the kinds of applications I think are mature. I think we'll see more and more acceptance of those applications, and it can span a variety of industries. But thank you for the questions.
Awesome. Thank you, David. This concludes our live question and answer session. Thank you to those who submitted questions, and if we didn't answer yours during this webinar, we'll respond via email. This upcoming Tuesday, come discover how you can make drastic improvements to your company's production flow and efficiency through automation. Canon will present how the use of 3D vision applications and robotic bin picking can solve the challenges of ROI, cycle time, reliability of a system, and more. Register now at www.visiononline.org/webinars. Please join us for our first virtual conference, AIA Vision Week, taking place May 18th through the 22nd. AIA is bringing you a full week of educational conference sessions, enlightening keynote speakers, and connections to the industry's top suppliers showcasing the latest vision and imaging technologies, all from your convenient computer, tablet, or mobile phone screen. Participation is free, and anyone working with vision and imaging technologies, or those who would like to, are encouraged to register at visiononline.org. Lastly, I hope you found this webinar to be interesting and informative. If you have any questions about the Association for Advancing Automation or today's webinar, please reach out to either David or myself via the contact information you see on the screen. As a reminder, this webinar has been recorded and an email with a link to the recording will be sent to you in the next 24 hours. Thank you again to David for presenting, Matrox Imaging, Lucid Vision Labs, IDS, and Teledyne E2V for their sponsorship, and to all of our listeners for your support. Stay safe and healthy, and have a wonderful day.